All right, let's kick this off. Hi everybody, my name is Laureano. I work at Domain, and today I'm going to be talking mostly about akka.net, but not so much on the how to do certain things within akka.net, because within Domain we actually did this into production, and what we implemented was a real-time clickstream event processing system. And this is more of a retrospective of what happened, how we approached it. And there's a few different things that we did during the course of our journey into reactive programming. So, as with everything else, I'll start with the beginning. We ran into a very interesting problem, which was, how many people here have batch processes that take more than a few hours to run every day? And how many of you have reporting at some capacity within the business? Now within Domain, one of the problems that we had is, as you know, if you're familiar with Domain, we have a lot of properties in both residential and commercial real estate. And one of the problems that we have there is that we might have hundreds of thousands of properties, but on the other hand, we can't afford to wait till the end of the day to see whether or not a particular property has the clickstream or the views or the inquiries that it needs. So in the first version of what we called our stats system, what happened was it was pretty much what you would expect from any traditional system. We collected all our events, waited till the end of the day, and we stored it inside of a SQL Server instance. And for a time, that was okay. And at the end of the day, what we would do is we would run a stored proc, collect all the stats for the day, and then by the time the agents would look at it the next day, everything was great. The problem was that was 5 years ago. The problem was that the scale of our growth was such that it was no longer practical to be doing this on just a daily basis, because as the more and more properties we had, there was a greater need to make things closer to real time as possible. So there's this one question we have to ask in this case. What was a better way to do this? Is it better to do one long batch process that would take 6 hours or an entire day? Or could we somehow split it into, say, 86,400 batch jobs in one day that take 1 second? So we did a bit of research and we came up with a lot of things, but the first thing that we found, or I found, was the actor model. And now, if you've been paying attention to Aaron's talks or Sergey's talks with Orleans, there's a couple of flavors of that. But along the way, the actor model poses quite a few, it actually solves quite a few problems that we weren't able to solve with the traditional stored proc model. First thing that we tried was doing async. We quickly found out that it became unmaintainable simply because, well, I'm a fallible human. I can't think past 10 threads. So we were looking for better ways to actually do this. And if you're not familiar with async, it's fairly straightforward, but the short explanation of this is it's basically a syntactic sugar over what is essentially the task parallel library. Now, it's fine if we were dealing with just a few properties, but in Domain, since we had about 100,000 properties and we had all these different clickstream events coming in at once, and when I say clickstream, I'm talking about when somebody does something with a property listing on Domain, whether it's click on, email a friend, or they want to look at the pictures, we want to record every single thing that they do. And this kind of clickstream data is really, really valuable because it gives us an insight into what the market wants. And in turn, we could take this data and use it to come up with better solutions for some of the problems that we're currently having at the time. So with async, the problem that we had was mostly around shared state. you could spawn up several thousand async threads, but you start worrying about whether or not you have deadlocks, whether there's some resource that you haven't released, and at the same time, it didn't really scale beyond a single machine. It's very hard to debug these sorts of things, simply because if you catch an aggregate exception, now you got to drill down into every single thread that fails, even though the C# compiler does do a good job over abstracting away a lot of the state machine logic that is in place. Now, with the actor model, we don't have to worry about those things. With the actor model, it's, as Aaron once said in the previous session, it's just as old as the concept of relational databases. And the idea here is that there's no locks. Second, we let actors fail and fail hard because we could easily restart them if there's any issues. And the other thing is that it scales very, very well to thousands of threads per machine. And in our case, we scaled it up to hundreds of machines in AWS. So we had thousands of threads not only go across one machine, two machines, three machines, but we put together an infrastructure that could tell whether there was a high CPU spike inside of a cluster. And we took it to the next step and made it closer to Erlang, because in Erlang, what they do is if there's what you can do is remotely deploy code. So essentially, within domain, what we did was combined akka, octopus deploy, and if there's any kind of situation where we sense that the CPU is spiking, we can provision 2 or 3 more machines within 10 minutes and deploy another set of actor systems and just keep it running. There was quite a few challenges here, and I'll go over them. But some of the challenges that we ran into was mostly around state and syncing state. And how do you sync that state across all those nodes as they spin up and spin down? For the actor model itself, it's fairly straightforward. And it works on a few simple rules itself. Every actor has one mailbox. And the only way actors can actually talk to each other is if you send one message between the actors. The other important thing about actors themselves is that they could spawn child actors. So how this works is similar to what you would see in an IOC container, where you push all your riskiest dependencies out to the leaves rather than leaving it at the core. So in this sense, what you would do is you'd start spawning child actors and push it all the way down until you have specific implementations that are localized, and it will prevent the entire system from going down. That being said, actors have, at least within akka.net, have this ability to supervise other actors. You get these nice little trees that when you send a message to the top level actor, it might delegate all the messages down to all of its child actors. In practice, what we've done is we've had these coordinator actors, and what they would do is we'd have one that would read off of SQS, we'd have one that would do calculations, and it worked very, very nicely because we didn't have to worry about failures because we didn't have this monolithic task parallel library that we had to worry about and parsing aggregate exceptions if it failed. The other thing, as I mentioned before, is the actors don't necessarily take down the entire system. Since we have child actors, there's a few things that you can do with akka.net that allow you to either restart failed actors, kill them off, or continue with the error and just keep going. The other thing to note with akka.net, and as well as the akka JVM, is that it's fast. It handles roughly around 50 million messages on a single machine. And one of the things that we learned the hard way is that with this kind of power, we had to scale back our actors because it was too powerful on our machines. There was one instance where We actually got a nice email from Amazon S3 because we turned it into a logging system, and we were doing about a gigabit a second of just log files, and then we had to scale it back. So this is a very powerful system that we have in place. Now, with Akka itself, it's pretty straightforward. So with actors being able to send messages to other actors, this is probably the simplest example that I could come up with. Now, a message in this case is pretty much any immutable reference object that you pass from one actor to the other. It's also worth mentioning that actors themselves are location transparent. So as long as you have the actor reference and you call a send to another actor, you never have to worry about where it is. The other thing is that with this class, as simple as it is, this is more of syntactic sugar. This is the strongly typed version. So if I go through the constructor here, you could see that I'm sending a string. In practice, you wouldn't want to send a string. You'd probably want to send something like an immutable class with no public setters, just to make sure that you could serialize it and have guarantees about concurrency and never have to worry about locking or any kind of threading issues. And as you can see here, this is pretty much an example of what you would do for an immutable message. You've got all public getters and private setters, and in Akka or Akka.net, what it does is it handles all the serialization for you. In some form or fashion, it would serialize this down to either JSON. I think the latest versions do binary serialization. You could always check with Aaron. And sending messages is really, really simple. So the tell method is you've got one message, and then the second parameter there is the actor ref or address. In this case, I just said self, just because I want to reflect the message back and process it. It's really, really that easy. The other thing that you should note is that with actors, there's this concept of an actor ref. The address itself, there's a few things here. The protocol is fairly straightforward, so it's TCP, because you want to send it over an HTTP connection. You have the name of the actor system, so that's just in case you might have more than one actor system inside of a machine. And at the same time, you also have the host name and port, as well as the path. Now, if we look back at some of the other diagrams where you had supervision, where you had /user/actor name, that's basically the path in the tree for whatever actor you want to talk to. So for example, if I want to say user actor name 1 and there's an actor under it called foo, it would just be /foo, and I'd be sending messages that way. So it's fairly simple to be able to address and send messages across the wire using this kind of addressing scheme. Now, the other interesting thing that we found out pretty quickly is if we wanted to do a kind of broadcast, you could do a wildcard-based broadcast just by using something called the actor selection. Now, with actor selection, what you can do is if you're in an actor at a certain point of a tree, the context object, what that does is say, from this point in the tree onwards, I could send these sets of messages. So in the same sense, you could send a message to an individual system, but you could also use actor selections to do wildcard broadcasts to child actors if necessary. Now, in the simplest sense, if you really wanted to create an actor system, it's one line of code, plus maybe the name of the actor system if I inlined it. In a production environment, of course, there's a few more configuration settings that you have to set. You could do that through either HOCON, or you could do it programmatically, which is what we prefer inside of an AWS environment. And the reason why we went with programmatic is that more often than not, when we deployed to these boxes in AWS, it became impractical to have to RDP into those boxes and make sure that they had the right configs. We wanted to make sure they're all homogeneous, but at the same time, we wanted to make it as zero touch as possible and still be able to function. Now, the syntax for creating an actor system is something that's been inherited from the JVM. And what this essentially means is this is analogous to what COM did back in the 90s when you said, I want to create an instance of an actor. Now, inside of the props.create is basically a lambda that tells aka.net how to create your actor, regardless of whether or not it is on your local machine or on a remote machine if you're going to be using clustering. So in the same way, once we created the actor, you could just do a tell on the actor without having to worry about where it is. At the same time, if I want to create a child actor, all I have to do is use context, which basically means that wherever you are in the hierarchy, you want to create a child actor of my child actor in this case. Again, the syntax is very, very regular. It's very straightforward, simply because there's not really a lot of code that you have to do in order to get it done. The one thing to remember in this case is that while you're doing all these things with actors, you never have to worry about locking. It's very, very safe to have private collections that are not concurrent collections, for example. You don't need a sync lock object. You can do whatever you want with it, provided that all your state is immutable and not publicly exposed. The other thing that's really interesting, at least from an architectural standpoint, is, does anybody remember Windows 3.1? Or, yeah. Or does anybody not want to remember Windows 3.1? So what we realized is that this is actually a degenerate, concurrent, cooperative, multi-threading distributed system. So basically, it's like distributed Windows 3.1 without the disadvantages. Because when you spawn actors, you're basically sending it out into the world with the assumption that nothing can break it because it doesn't expose any state. The other thing to remember is that with these actors, you can just keep doing all these things in parallel, and you never have to worry about how are they going to interfere with each other. And later on, I'll show you how we could spawn it up to several thousand threads, but still be able to treat it as if it were a single thread and not have to worry about it. Of course, not everything goes according to plan with aka.net actors. When things start to hit the fan, the problem is that how do you handle errors when things happen? Now, there's something from the original paper from Carl Hewitt, which is this idea of the error kernel. And how this works is that the errors bubble up from the child nodes all the way to the top. And in these child nodes, whenever things go wrong, the parent actor has a couple of choices about what they want to do in case things fail. In general, there's really two strategies. You could come up with your own custom strategy. The first strategy is going to be that you could kill off the actor that caused the failure as a parent actor, or what you could do is you could kill off all the child actors and restart. There's also the option to resume, but it's like VB6 on error resume next. You don't want to do that because you want to make sure that when it fails, you restart it and keep it in the right state, and that's what we've learned. The other thing is, so up to this point, I've been talking about how to handle a single machine, multi-threaded scenario. But how do we handle cases where we want to go distributed? Because it's great, we want to use aka.net, we want to be able to spawn any number of threads we want, but how do you make it so that this works on a very large scale? So for us, we had this huge problem of one megalithic database server that just couldn't handle the load. We would get thousands, millions upon millions of events per day, but we couldn't process it all. And now we had this challenge where we wanted to do it in real time. So the first thing we can do when we start talking about how to scale up with the single machine is that there's these special kind of actors called routers and router pools. Now, with a round-robin pool, what that means is that it is a specific type of actor that spawns thousands and thousands of other child actors of this type, depending on the load. So what this means is if I send a message, the message will come in through the router. There might be up to 1,000 instances inside of that router actor, and it'll just go through every single one of the actors in a round-robin fashion until every single one of the messages are handled in parallel. So the nice thing about this is that I don't have to worry about managing state. I don't have to worry about what to do with every single actor, because this is kind of like classic object-oriented programming, where every single class is responsible for its own state. Every single actor is responsible for making sure that its child actors are behaving properly. And if it doesn't, then the router will kill off the child actor, depending on the strategy, of course. Now, as I mentioned before, you don't have to worry about locks, and you don't even have to worry about actor allocations, because the round-robin routers have a parameter in there that say what's the minimum number of actors you want, and what's the maximum number of actors that you want to spin up. So in domain, what we did was, for a single machine configuration, we started getting all these messages that would flow in. And obviously, if you're thinking of an actor as a single-threaded actor, you don't want to handle this on one thread. You want to spin this up about 1,000 actors so that we could potentially process them all in parallel. So there's a few other pool router types, but this is more of an exercise for Google. There's random, which doesn't make any sense because we want to evenly distribute the load. There's consistent hash routing, which is more useful if you're going to go down the path of clustering. And then there's a small mailbox, which is just trying to route the messages to the actor with the least amount of activity. Now, I know the code is fairly small in this case, but this is pretty much all we needed to do to scale up to thousands of threads per machine. This is just a simple PowerShell script that starts up an actor system 5 times on the same machine. There's nothing magical about this, and that's the point. We didn't have to do anything special to do that. The interesting part is that we were able to scale up our capacity in 2 ways. We could either deploy to more machines or run more instances of the actor system on a single machine so that we see the CPU spike up to 100%. Now, the interesting part is, how do we get these actor systems to work together? There's a few, depending on what your requirements are, there's a few ways you could do this. Now, the first way, which I don't recommend, is really going with aka.remote. That's really just peer-to-peer connecting 2 actor systems together with no redundancy at all. And that's what Akka cluster is based on. And Akka cluster is a good tool in the sense that it's completely decentralized. It's a peer-to-peer node cluster that elects its leaders, and there's quite a bit of gossip between the nodes. But there are some drawbacks, and of course, we'll go over that as well. The one we chose that was most favorable was the cloud-based queues. So we're on AWS. We use SQS to do batch jobs, and what we found is that in most cases, AWS is reliable, unless it was a couple months ago where it did go down for a couple of days, but for most of the time it was perfectly fine. Now, Akka remote. So as you can see here, this is just a simple diagram of all the states every single node is inside of Akka cluster. So what they do is they start talking to each other, and the algorithms basically determine which nodes are connected within the system. And if they're not able to talk to each other, they actually talk through an intermediary node so that they could be all in sync. Now, clusters themselves make it so that every single node inside of the cluster behaves like a large monolithic system. In most cases, it does work well. There are systems like Cassandra, React, and whatnot that do this. But what we found inside of domain that this doesn't really scale well, at least for our requirements. And given that fact that we would have lots of machines spin up and sometimes disappear depending on what the CPU load was. So again, there's a few disadvantages here. The number one disadvantage within Akka cluster is the fact that if, for some reason, let's say you had 5 nodes, and in those 5 nodes, they were behaving as part of a cluster. And in our environment, AWS detected that the CPU dropped below a certain threshold, and we could kill off 2 boxes, or let's say 3. If you kill off enough boxes within a cluster, somebody actually has to manually intervene and tell the rest of the remaining nodes that the cluster and all the missing nodes have been removed, which is quite messy because it's not very cloudy, because we want to do this in such a way that doesn't require any kind of human intervention. This should just work. So I took the time to just draw a very crude diagram of what the flow of the data is within domain. So we have a click stream where people do things like send inquiries. We say, for example, you might have somebody click on a nice house and say, I'm really interested in buying this property or renting it, and I want to contact the agent and figure out whether it's still available. We need to record every single thing that everybody does on the domain website, and that's what's happening inside the click stream. Now, the tricky part about this is that we have to save this at roughly around the same time we have to do aggregates for every single property on the domain website. So you can imagine if there's 1 million properties that are active per day, we want to come up with the total number of inquiries, how many times somebody clicked on something, and have those metrics available at any time, and they should be up to date within 10 or 20 seconds, or at least something much faster than the 6-hour or 12-hour latency that we were experiencing in the beginning. So how this works is that we found that we had to save it in a couple places. We had to save it in the S3 so that we could export it into Redshift. And at the same time, I didn't put it on the diagram, but we had to save it into Elasticsearch, because what we found is that even though in theory, if we had 2 copies of the same data, one going to Elasticsearch, one going to S3, they should be identical. At the end of every day, we always found that there were some messages that are dropped. So to prevent any kind of loss, what we would do is we'd compile a hash list of all the events that have occurred within a day and compare it to what was exported in S3 and compare it to what we had in Elasticsearch. We would do a diff, and then once we figured out which properties were affected as a result of the loss of that diff, we do an end-of-day recompute to make sure that we have the right numbers and we still have the eventual consistency that we wanted without sacrificing accuracy or losing anything, which was very, very important for us. Now, the other thing that we found is that Amazon SQS is really, really good at distributing workloads. At first, we were going to go with Kinesis, but the API, depending on what SDKs you use, it was a bit raw, and we needed something really simple. We wanted to reduce the consumption and posting messages down to a single HTTP GET or POST in this case. So that's why we went with Amazon SQS. Now, is everybody here familiar with AWS SQS, or how many people here use Azure? How many people here use AWS? So it's about half and half. So when we were looking into SQS, it had a really interesting property where there was something called a timeout. an invisibility timeout. And the idea was that if you pulled a message out of SQS, you could set a time limit where it would become invisible. And if you didn't delete it, it would pop back into the queue as if it was never processed. Now, normally that doesn't seem like a lot, but for us, it had an interesting side effect because we could process jobs in parallel. And if the jobs failed, we didn't have to know whether they failed or not because we would know that they failed if they were still in the queue. So if it failed the first time and an actor didn't delete the message off of the queue, it goes straight back into the queue and we'd have a different actor system process it all over again. And it would do it completely in parallel. Now the best part about this is that when we had 5 or 6 different actor systems, they didn't need to talk to each other at all. There was no sync time. When we had cases where we're about 1 million messages behind, it became a really easy scenario to handle because now all we had to do is create another set of actor systems or spin up about 5 or 6 more machines, and then we were back in business and they were able to process the load. There were a couple trade-offs, of course, because with this kind of amount of power, we could easily take down any database server. So as you can see here, the diagram pretty much shows what I was talking about. You have all these data sources that post a clickstream event, which triggers an aggregation request that we'd stick inside of the queue. On the blue side, we would have an on-demand aggregator that would just spin up, pull the message off the queue, pull all this data into a snapshot in Elasticsearch, do the computations, and then throw it away and save the result. So it was a really interesting scenario because we didn't have strong consistency, but we did have eventual consistency that fit within the latency period that most people were expecting at the time. Because at the time, agents were expecting things to happen within 24 hours. If we get away with doing this within a couple of seconds and they notice a few glitches here and there, it's not a big deal. The fact that we were also using event sourcing where we might save events straight into Elasticsearch and there might be inconsistencies between 2 sets of actors trying to do the same aggregation was not a big deal because we never really deleted any data at all. They would get a different snapshot and maybe one would overlap the other, but we compensated for that by doing end-of-day snapshots where we would figure out which properties were active and do one last calculation so we have the final sense of consistency that we were looking for. Now, from an academic standpoint, you might be asking, so what's the difference between clusters and grids? And it's actually quite simple. I mean, I don't have to go through this list, but what it comes down to is that clusters require consensus. When things go bad inside of a cluster, all the nodes basically say, are you okay? Are you okay? What happened to this? Node A, what happened to node B? Is that node okay? But within a grid, we could linearly scale by adding 5 or 6 more nodes. And since every single actor system is behaving as if all the other actor systems don't exist, it's very easy for us to scale up and be able to push new nodes out without even have to worry about this. So our sample grid configuration looks like this. So in a classic grid configuration, you would have a master node that would start handing out jobs. But in this case, we use SQS. Because what happens is that when we push something into the queue, one actor pulls one message off the queue at a time, just to be fair. And we might have 20 actor systems that are pulling one message at a time and processing it. So every second they pull one message and process it. And I wouldn't know where it's actually occurring on, but it doesn't matter. I don't even need to know whether it's successful or not, because if it fails, it drops back into the queue and it's processed all over again. Now, for EC2 instances, this is the interesting part. Depending on the load, we fixed it to a minimum of 2 instances just so we had redundancy. But if there was a high amount of traffic, we would scale up to 20 nodes and that would come out to be 100 actor systems in parallel. Now, with this kind of scalability, this is not something you could easily pull off in cluster. With cluster, it wouldn't be able to handle the fact that you're taking out and putting in so many nodes at once, depending on the demand, in which this is what we needed. The other thing that we have is that we actually, in Domain, we have this custom tool that we built into Octopus, which is what we call the robot army, where we could spin up entire clusters in a line of code and deploy certain versions of Octopus, deploy packages straight into these machines without even having to worry about any issues. I mean, in most cases, what we were able to do is hit the button, go up, get coffee, come back, and everything was all good. Now, in this scenario, when we were handling clickstream events, what was happening was the AWS would detect a high CPU demand. The robot army would respond by creating 2 or 3 more instances and then push the actor systems out to these boxes, and then all of a sudden you see this massive CPU drop that would be able to handle the click streams as they came in. Now, compared to, say, your traditional relational database, this was way better because we found that we had a latency of about 10 seconds, and that's across any number of properties at once, and this was doing this hundreds and thousands of times per second. The other interesting but notable thing that we did was we logged to Slack. So in cases of failure, one of the things that we ran into is that since all these systems are completely disconnected, we need to be able to log this information to a centralized location. So Slack was the best place. So we just created a custom channel with just a bunch of alerts in it, and then we were able to push out all this information there. Now, for grid actor roles, the idea behind grids was something I pulled out of swarm intelligence AI. So if you ever look at how bugs or ants behave, you'll see that within a colony, they always follow a very simple set of rules. By themselves, they don't seem very smart, but once you start to multiply them to larger numbers, they start doing pretty amazing things. And in that sense, that's what we did with the grid. So there's a few things that we did. So for pulling aggregation requests off the queue, we had one actor that did it, and then it would forward it to all the other actors that would process it. We also had another actor that would just fetch the snapshot for a particular property and all the clickstream events that occurred during that day, and then do the calculation, and then we just dispose of the actor naturally. And the other thing to keep in mind is that when we moved events from SQS to S3 buckets, we also had actors for that as well. We also had different actors that would do this kind of reconciliation where we would look at what we had in Elasticsearch, and at the same time, we would also look at what we saved into S3, because ultimately what we were trying to do was do an export into S3 and have it imported into Redshift so we could do analytics on it. So on one hand, we had a data warehousing solution that was the ultimate goal, but at the same time, we also want to maintain consistency in what we're exporting and calculating in real time at the same time. So there's a few things that we learned when we were going through this process. Now, for CAP, one of the interesting parts that we found is that when we were doing these kinds of aggregations, we were actually sacrificing availability. We had weak consistency, and we did have strong partition tolerance. It was a really, really interesting case because the only form of consistency that we actually had was what we were storing in Elasticsearch. And if you do a bit of research in Elasticsearch, you'll know that it's not entirely strongly consistent, but it is eventually consistent. And that brings me to the first point. Now, given that you could, with this kind of capability with Akka.NET and working with multiple nodes, you could easily take down any server. That is Elasticsearch, that is your relational database, you name it. With enough machines and enough actor systems, you could pretty much do anything you want with it. So for us, what we learned is that it was more of an exercise in restraint rather than trying to throw all this capacity at it, because even though we had hundreds of thousands of threads that could go at once, we were ultimately bottlenecked by I/O at the end of the day. Now, the other interesting thing, but it does sound a bit contradictory, is that grid actor systems are great if they store absolutely no intrinsic state, that is long-term state. When we were doing these kinds of calculations, what we would do is we'd pull in the snapshot, and it was consistent for that moment, calculate it, and then throw it away. Now, what that guarantees is that we could pretty much kill off any actor, and the next actor that came along to process the property itself wouldn't have to worry about whether it was wrong or not, because number one, we never deleted any events. We're using event sourcing. Number two, we never have any kind of inconsistency problems, because towards the end of the day, we do one last calculation when we have everything, and that would guarantee that our numbers were correct. The other thing to keep in mind is that we had to operate on the assumption that any one of our machines could just vanish at any minute. And that's because of auto-scaling both up and down. And this is where the partition tolerance part comes into play. If we don't have any state, and we keep the state in an external node, which is effectively Elasticsearch, we don't have to worry about any kind of consistency problems. So there were some pretty interesting trade-offs, because essentially every time we would get a new event, we'd start querying events back into every single actor, which there is a bit of overhead. But it was a good balance for us, because we were finding that we still maintained consistency, we still maintained accuracy, but it did take a while for everything to line up, and that was more towards the end of the day. But the side effect there is that when agents started looking at their reports, they could just refresh the page and do something, and they could see it happen in real time or close to real time. And that's what we were looking for, because we came from an environment where we were waiting an entire day just for somebody to click on something and the number to go up. Now we're in a state where if somebody just clicked like 4 or 5 times and did anything, we'd be able to see it within a minute or so, which was like infinitely better than where we were. Now, it goes without saying that if you have an elastic cluster of actor systems, you need to have a matching data source that could scale up with it. In our case, we found that S3, because of how it's built, could scale up well with the demand. At the same time, Elasticsearch, depending on your instance type, can scale up along with the number of actors that you have. So depending on how many actor systems you have, as well as Elasticsearch instances, and whether or not they auto-scale, if we start hammering the server, what we have seen is that we would spawn up another Elasticsearch instance, and it would be able to take the load. And once the demand started to go down, what would happen is they'd pull the Elasticsearch instance out, but it would still keep running. And that was really important for us. The fifth thing that we learned during the storm from hell about a month and a half ago was that it's better to make sure that even though you think that everything's going to be okay, you always have to assume that you're going to have some sort of message loss that occurs. So if we have all these events coming in, even if it's 1 in a million, if we have 20 million events come in, you're still going to lose 20 messages. And the problem with that is that within domain, we can't afford to do that, simply because one of those messages could have been a message to an agent saying, hey, I'm really interested in your property. That could have been a multi-million-dollar sale, depending on where in Sydney or any other capital city that's selling property. So we wanted to make sure that we don't lose anything. So the interesting story here is that when the site went down, because AWS went down in the Sydney region, we noticed that there was a lot of data that we had within Elasticsearch that was not in S3. We lost 3 days worth of data. Now, 3 days worth of clickstream data is nothing to laugh at. It is a horrible, horrible situation. But since what we did is we came up with making sure that we created 2 copies of the data. Every time it came in, we were able to use that diff to fill in the blanks. It took us forever to do it. It took us about a day or 2 to do it, but we were able to fill in those blanks. So the important thing to remember in this case is that as long as you have a backup and you could have the same kind of eventual consistency where you could merge the 2 sources and fill in the blanks, then you should be all right. But the lesson to take away from this is the fact that it's never keep all your eggs in one basket, because you will lose it at some point in time. The other thing that I probably didn't mention in this case is that for those of you who are interested in the differences between how akka does things and Orleans behaves, it's really more of a difference in philosophy. Now with akka, the difference between the 2 is really manual versus auto. In Orleans, there's this tendency of let's take care of everything for you, and you basically treat it as distributed C#. And that's fine for some people, but in this case, if we were to do this kind of scaling, it just wouldn't work for us, because if we take machines out and all of a sudden, I don't think the Orleans cluster would do exactly what we want to do, and it wouldn't allow us to tweak it in the same way that we would be able to do in AWS, especially considering they were in Azure. So, but aside from that, I'm pretty much open to any questions, because I know this is, how are we doing with time? Yep, cool. So what I'm going to do is, this is more of a Q&A thing, because I know that I didn't really go over the how-to side, though, but there's a lot of interesting stuff that we came up with inside of Domain. So the other thing I would also plug is that in the same room, in the next session, are going to be 2 of our DevOps engineers who pretty much pulled it off. And they're going to be talking about how they do auto-scaling in excruciating detail in AWS, including all the PowerShell scripts, including how they hook into Octopus. So please, 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 if you can, watch the session, because it's really worth it. And I did hear a rumor that they will open source it very, very soon. So all the tools that I've mentioned here are going to be open sourced. So with that, thanks for coming. I'm pretty much open to any questions.
Might be a large question to answer, but can you talk a bit about the design patterns around?
Yeah, so for the actors themselves, there was a heavy amount of pub/sub. So how it works is when we were pulling things from SQS, we'd have one actor that would keep on polling SQS for a certain amount of messages on a timer. And every time it would send something out, the way it works is that we had a base class that was basically did all the pub/sub, where it would just do a tell. And it would keep a list of actor refs. And it would go through that list and just basically do your standard pub/sub and then forward it over. The big one, of course, that I did mention before is the competing consumers bit. There were a couple instances where we tried to farm out a lot of the functionality just to make sure that if we had failures, it didn't really take down the whole system. But I do have to mention that one of the problems that we did run into is that if you scale the actors too much, you start running out of memory. One of the problems is that if you pull in too much information at once, you will basically run into an out-of-memory exception and kill off all the actors in every single actor system. So it's a balancing act, and it's really about tweaking and making sure that you have the right settings, and that's just part of akka.net. And what else? Yeah.
So you were talking about message routing before.
Yep,
So Akka's, I don't know if it's using Erlang or not, but
it's definitely not using Erlang. Yeah.
so I guess Rabbit has this thing of an exchange where you can actually duplicate messages across your queues.
Yep.
Is Akka doing the same thing? Can you duplicate your messages around?
Well, in this case, like I said, Akka is really manual versus auto. The functionality for you to do it is there. So it's more of an infrastructure tool rather than giving you something that does everything. Because I would have to say that Akka is more of a true to what, it's a really true implementation of the actor model, that they don't really try to hide anything. And in that sense, if you're familiar with CAP, you're very confident about how you're going to use it, then you just use what you need and you just don't touch the ones that you don't need. And so to answer your question, there is no kind of duplication. In our case, what we had to do was we did have to create an actor that would just push to two different places. One would save to Elasticsearch, one would save to S3. But that was pretty simple to do. And we controlled all the instancing. We also determined how many actors we'd spin up. So overall, it's just that fine grain of control that we needed. And in this case, you can't really do a grid in, say, Orleans. It just doesn't make any sense because that's not really what they want to do.
Yeah, I was actually just going to touch on what you spoke about before with Orleans versus Stacker, and you said you wouldn't be able to, when a node went down with a cluster, it wouldn't work as well in Orleans or something to that measure. As someone who's like evaluating both sort of options, what are the major disadvantages to going with Orleans outside of that?
Well, I guess it really depends on which philosophy would fit your requirements.
Majorly different though?
They're very different. So with Orleans, you don't control any instancing. You don't control the lifetime of an actor. You just assume that somewhere in that black box is an actor instance that you could maintain and send messages to. And they'll guarantee that it's there. But if it goes idle, there's a good chance it might get killed off and you have no control of it. It's kind of like garbage collection. Well, they have this terminology where they say they hydrate or dehydrate actors, where you put in plugins and what it would do is deserialize itself, and then once it's activated, then it would try to rehydrate itself and handle the message as if it was always there. They call that virtual actors. In Akka, if you go with clustering, the trade-off is that they don't have any cluster metrics, so you wouldn't be able to directly distribute the load across five nodes. Whereas in Orleans, they are very smart about making sure that if you've got 5 nodes, it'll equally distribute the work. So it depends. If you want to do like transparent, like distributed C# without having to worry about the low-level details, then that would work in Orleans. But if you wanted to make sure that you could scale up without any hiccups, then you really have to go manual, and that's what we did. Anything else? Oh, that's an easy crowd. Thanks for coming. It's for Manning. You could check this one out because it is an intro to Akka.net, and it's coming out pretty soon, if not out already. So just have a look at this one. You could also check the references here. And as I mentioned before, the domain DevOps guys who do all the magical stuff, they're going to be doing a very in-depth session on how they actually do it and how they move domain into like full auto DevOps and Octopus. So please check that out. Thanks again.